Hello guys, welcome to Physics Grad. In this video, our main topic of study will be Galileo's relativity principle. And under this, we are going to mainly study about something known as frame of reference. So we are going to study what do you mean by frame of reference and what are the different types and so on. Alright, so let us begin. So the first question is, what do you mean by a frame of reference? Well, this is nothing but an abstract mathematical construct. Okay, it's an abstract mathematical construct or formulation with respect to which all measurements are performed. So with respect to which all measurements are performed. So this measurement of what? Measurement of any physical quantity. For example, position, velocity, acceleration, etc. So this is a mathematical construct. So this is something which is created by us and not something which is already present in the universe. And that is something important that we must remember. So for example, a familiar example would be a frame of reference. So I'm going to denote this as FOR from now on for convenience. So a familiar example would be a frame of reference defined using the Cartesian coordinates. So using the Cartesian coordinate system. So how do we define a frame of reference using Cartesian coordinate system? This is something which is familiar to all of us. Now this is formulated by using or making use of 4 points in the three-dimensional space, out of which one of them represents the origin and the other 3 represent the ending point of unit vectors which define the 3 perpendicular coordinate axes, and we usually denote them as x cap, y cap, z cap, or I cap, j cap, k cap, and so on. But along with this, we also consider the time axis. So this is an example of frame of reference, and obviously this is something which is created by us and you don't see this in the universe. What I mean to say is that you don't see anywhere 3 unit vectors along 3 different axes or an origin point in the universe. So this is purely an abstract mathematical formulation. And this origin is not constrained to be at a particular point in space. It can be anywhere. So this is an example of frame of reference defined using the Cartesian coordinate system, which many of us are already familiar with. Now, since all measurements are done with respect to a frame of reference, our first job before we start any calculations regarding the mechanical properties of a system is to choose a frame of reference. So this implies we must first choose a frame of reference. All right? But the next question is, how do we choose this? What frame of reference do we need to choose? How do we answer this question? So this question is difficult to answer because there are infinitely many choices. Alright, so there are infinitely many choices. So what I mean by this, for example, is that if you consider this particular example, we can place the origin at any point in space and correspondingly get a separate or a different frame of reference. And therefore, there are infinitely many choices for choosing a frame of reference. So how do we make a choice? Also, once we choose a particular frame of reference, in general, the laws of motion will have different forms in different frame of references. So we'll have different forms in different frame of references. So that means that if I have two different frame of references, I need not have the form of the laws of motion the same in both the cases. Then how do we choose which is the correct frame of reference? And the obvious answer would be we need to choose. Therefore we need to choose a frame of reference with respect to which the laws of motion take the most simplest form. Otherwise, we will simply make all of the calculations more complicated. So therefore, we will choose a frame of reference with respect to which the laws of motion take the most simple form, because this is the most reasonable thing that we can do. Okay? Why? Because different frame of references will have a different form of laws of motion, or a different structure of the equations which describe the laws of motion, and in some frame of references these equations will be complicated, whereas in some other frame of references these equations will be quite simple. So therefore, naturally, we should try to choose a frame of reference with respect to which the laws of motion take the most simplest equations as possible. Alright, good. Now, one way to ensure this is to make sure that the space and time is homogeneous and isotropic. So how do we ensure that the laws of motion are in the simplest form? One way to ensure this is to make sure that space and time are homogeneous and isotropic. So what do I mean when I say that space and time are homogeneous? So what this means simply is that if I have one particular point in space and any other point in space, then there is nothing special about this point as compared to this point. So there is nothing special about, let's call this A and let's call this B. A as compared to B. That is the meaning of homogeneous or homogeneity of space. So what I mean by this is that if you consider a particle which is under, or let's say the simplest example would be the case of a free particle which is not experiencing any kind of external force, then its behavior is going to be the same at point A and in point B. So its behavior does not change when you go from point A to point B. So the behavior of a mechanical system which is experiencing some sort of constraints and forces is not going to change when with position. So homogeneity implies that the mechanical behavior doesn't depend on what point in space we are considering. Okay, so it doesn't depend on what, or more correctly, which point in space we are considering. Or in other words, mechanically speaking, every point in space is equivalent. All right, so every point in space is mechanically equivalent. Okay, so that means that if the particle is free at point A, then, or in other words, if the particle is not experiencing any force in point A, then it will behave as a free particle. Similarly, even if you consider point B and it is not experiencing any force in point B, even then it is going to act as a free particle. So its behavior is not going to change if you consider two different points in space. Okay, so that is the meaning of homogeneity. Okay, so what about isotropic? What do you mean by isotropic? So isotropic means that there is no special direction, or so in this case, so when you consider isotropic property, so this implies that all directions in space are mechanically equivalent. So all directions in space is or are mechanically equivalent. Again, when I say mechanically equivalent, it simply means that if you consider again a system or a particle under certain mechanical conditions, its behavior is not going to change if along two different directions. Okay, so for example, if you consider a particle which is free and moving with a constant velocity along a particular direction, then the behavior of this particle is the same as a free particle which is moving in this direction. So mechanically they behave the same. So that is the meaning of the isotropic property of space. So similarly, time is homogeneous, which means that a particle is going to behave mechanically in the same way in different instances of time. So there is nothing special about two different instances of time, just as we saw that there is nothing special about two different points in space, right? And since time is only along one line, its dimension is just one, so it doesn't make sense to talk about isotropic property of time, because there is only one direction here. There are no many directions in the case of time. So time is just homogeneous and space is homogeneous and isotropic. So one way of simplifying our equations governing the laws of mechanics is to ensure that the frame of reference that we choose is such that with respect to that frame of reference, space and time are homogeneous and isotropic. So how does this ensure that the equations are simple? It is just because of the consequence that 2 points in space are mechanically equivalent. So the laws of mechanics is not, or the equations of equations which govern the laws of mechanics is not going to change when you change the position of the particle from one point to another, or more precisely, two different points in space are mechanically equivalent. And same goes for isotropic property, wherein instead of considering 2 points, we consider 2 different directions. All right. The next natural question that can arise is it really possible to construct such a frame of reference? So, is it possible to construct such a frame of reference? What guarantees that we can construct a frame of reference wherein, with respect to which, space and time are homogeneous and isotropic? How do we answer this question? Because there are infinitely many choices which are out there to choose from. And the unfortunate part is that there is no way to answer this question in a purely mathematical way. So how do we proceed from here? So this brings us to the postulate of Galileo's relativity. So to proceed from here, we need to postulate. Okay. So a postulate means that it's a statement without any mathematical proof. Okay. So we need to study, or we need to postulate the existence of such a frame of reference. That's the only way we can proceed, and then experimentally verify that such a frame of reference actually do exist. So let me state the postulate of Galileo's relativity. Okay. So unfortunately, there is no mathematical way to construct a frame of reference such that space and time are homogeneous and isotropic. So what do? We simply postulate that there exists such a frame of reference and then experimentally verify it. Okay, so that is nothing but the well-known scientific method. Okay, so what does this postulate say? So this says that there exists a frame of reference with respect to which space and time are homogeneous and isotropic. Okay. So since this is a postulate, there is no proof for this statement, unfortunately. Okay. Now, such a frame of reference is called as an inertial frame of reference. So this is important. So what is an inertial frame of reference? It's a frame of reference with respect to which space and time are homogeneous and isotropic. Okay, good. Now that we have learned what an inertial frame of reference is, let us look at it in another perspective. Okay. So since we have already described that an inertial frame of reference will imply that space and time are homogeneous, this implies that if you consider a free particle, okay, so how do we say this? A free particle, so a free particle which is at rest at some instance, all right, will remain at rest always. So this is a consequence of the fact that time is homogeneous, because a free particle will behave the same way in two different instances of time, and since it behaves like it is at rest at some instant of time, it must continue to be at rest in the rest of the time instances. Okay, so that is what this statement says. So therefore, in an inertial frame of reference, a free particle which is at rest at some instance will remain at rest always. Okay. So with this information, we can now start guessing how the Lagrangian for a free particle must look like. Okay. So we can draw some conclusions about the Lagrangian for a free particle. Okay, since the Lagrangian describes a free particle's mechanical behavior, as we have seen in the previous videos. So the first information that we have is that since space and time are homogeneous, okay, the free particle's behavior is not going to change with different points in space nor with different points in time. So that means if it is at rest, or it is moving with some constant speed, it is going to behave the same way no matter at what point you place that particular particle, or no matter at what instance of time you are observing the particle. Okay, so this means for a free particle, remember, okay, so for a free particle, the Lagrangian must be independent of the position or the generalized coordinate q and time. Okay, so since we are talking about position, we might as well write this as the position vector r. Okay, and secondly, since space is isotropic, so this implies that there is no preferred direction in space. Okay, all directions are mechanically equivalent. So therefore, since L is a function of R, V and T. Now clearly V is not going to depend, or so when I say dependence, it means its behavior, okay? Because V is defined as dr by dt, we can say that the velocity, just by knowing the velocity, we do not know what is the time at which the particle is having that velocity, or what is the position at which the particle is having velocity, and therefore obviously V doesn't depend on position or time, it just depends on the rate of change of position with respect to time. Okay, so V doesn't depend on R and T, but instead it depends on dr by dt, that is the slope of R of t curve. Okay, and since space is isotropic, and since L doesn't depend on R or T, it must somehow be dependent on the velocity alone. It must be a function of velocity alone. All right, and since the space is isotropic, all directions are equivalent, so it should not depend on the direction of the velocity. So this implies L doesn't depend on direction of V. Okay, so that means it can only depend on the magnitude of the velocity. So therefore L depends only on magnitude of V. Okay, so now it all comes down to how do we exactly define this magnitude of velocity. One way would be to take the dot product with itself, and that will give V square, that is the speed squared. Alright, so this is one way of defining the magnitude, and you can argue that magnitude information can also be got by taking the mod, or I don't know, V power 4 or any even power and so on. Okay, but at this point we are going to say that L is a function of V square. Okay, and the justification for this will be given in the next video, which I'm going to upload, which will mainly discuss about how to get the Lagrangian for a free particle. Okay, so for now we are going to say that L is a function of only the magnitude of velocity, and we say that this magnitude is defined, or we say that we can represent this magnitude as V dot V, which is nothing but V square, and therefore we can write that L is a function of V square. Okay, now if you apply the Euler Lagrange equation, we see that since L is independent of R, this particular part will be 0, and because of this the total derivative with respect to time of the partial derivative of Lagrangian with respect to velocity must also become 0. Okay, so this particular term is a partial derivative of a scalar. Remember, Lagrangian is a scalar with respect to a vector. Okay, now if we represent position vector and velocity in the Cartesian coordinate, this will be nothing but dou by so this will be dou L of V square by dou Vx x cap plus dou L of V square by dou V y cap plus dou L of V square by dou Vz z cap. Okay, so this is a vector. All right, and Vx, Vy and Vz are the x, y, z components of the velocity. Okay, now since this is a function of v square alone, okay, so I can write this as some a v square plus some b. All right, so what does this mean? This means if I apply these operations, I'm going to get dou L by dou V as equal to 2AVx x cap plus 2AVy y cap plus 2AVz z cap, which is nothing but 2A times V. All right, and d by dt of dou L by dou V is nothing but d by dt of 2AV, which should be equal to 0, vector V. Okay, and that is this result. All right, now this can only happen, okay, this can only happen, so this implies V is a constant, which is nothing but the condition or the law for a free particle. So this is nothing but law of free particle, or better known as law of inertia. Which in turn makes our assumption that L depends on V square more, more concrete. All right. Okay. Now, because of this, it is easy to see that, so if this is our initial inertial frame of reference, and the particle is moving with velocity v, so I'm going to call this frame of reference as k. I'm going to name the frame of reference as k. Now, if I consider another frame of reference, k dash, which in turn is moving with respect to k with some velocity capital V. Okay, so k dash is another inertial frame of reference which moves with respect to the initial inertial frame of reference k with a velocity capital V, with relative velocity capital V. Now, if we observe the same particle from this particular frame, what will we see? We will still see that the particle is still moving with the constant velocity, and therefore we can conclude that even when we change, okay, so therefore if we consider another inertial frame which is moving uniformly in a straight line, which means there is no acceleration between k dash and k, which is moving uniformly in a straight line with respect to the initial frame, then what we observe that the particle still obeys V equals V dash. Okay, V dash is the new velocity with respect to k dash is constant. So this implies that the law of inertia has not changed when we changed our inertial frame. Okay, so therefore law of inertia is the same in both frames, is the same in both frames. Further, experiment will show that the frames of references which are such that they move with respect to each other with the constant relative velocity are all entirely equivalent in all mechanical aspects. Okay, so if we consider different experiments and formulate the mechanical laws, we will see that all of these laws are equivalent with respect to any of any of the inertial frames which are moving with respect to each other with some constant velocity. So experiment, okay, shows that these inertial frames, okay, these inertial frames moving uniformly with respect to each other, okay, are entirely equivalent in all mechanical aspects. Okay, and therefore, since this particular velocity can be chosen to be of any value, that is, this velocity can be chosen to be of any value and direction, we have infinite possible choices for k dash. Okay, so infinite choices, and this finally brings us to Galileo's relativity principle. So what does this principle say? It says that laws of mechanics remain the same at all inertial frames. Remains the same at all inertial frames. And this is a very important law in the establishment of classical mechanics. And since there are infinitely many choices for such frames, by the way, the frame k dash is also inertial because with respect to k dash also we will have space and time to be homogeneous and isotropic, and since there are infinitely many choices and in all of these frames the laws of mechanics remain the same, this implies there is no absolute choice for inertial frame of reference. And this is a very important result. This means that there is no special frame of reference which is present in the universe which we have to use. We can choose any inertial frame of reference. So there is no absolute choice for us. Okay. Then how do we describe, or if you consider two different inertial frames, how do we describe these equations which govern the laws of motion in these two different frames, or how do we transform the equations from one frame to the another? And this brings us to Galilean transformations. which basically says that if you consider the frame of reference k and k dash, where k dash is moving with velocity v or capital V with respect to k, then the relationship between the position vectors in the two frames will be the following. Okay, this is basically because of the definition of velocity being the derivative of position with respect to time. From that, it is straightforward to get this result. This is the first transformation, and another important thing is to note that t is equal to t dash. Okay, and this is true only in Galileo's relativity and not in special relativity. Okay, so this is not true in special relativity, because in that, how you measure time will depend on what frame of reference you are observing a particular particle or a system. Whereas in Galileo's relativity, we do not bother how, or we say that, the same amount of time has passed with respect to both the frame of references when you consider the same, when you are observing the same mechanical phenomena. Okay, so that is what this particular transformation say, and these two transformations together form the Galileo's transformation equations. Okay, and therefore mechanical equations, okay, to summarize, mechanical equations are invariant under these transformations. Okay, mechanical equations are invariant under these transformations. What I mean by that is that the form of the equations remain the same. Only thing that will change is an added phase. So by phase I mean there is a displacement term to the position vector, and obviously there is no change in time, and therefore the form of the mechanical equations are going to remain the same, and therefore the behavior of any mechanical system is going to remain the same when you observe it from two different inertial frames. Alright, I hope that this much is clear, and that's it for this video. Thank you for watching. See you next time.